as we get started. I just figure out. Okay, cool. Rightio, so let's quickly look. So the last one was mostly about just basically speaking with residential clients or prospective clients, just to, a lot of time they'll approach you about geo, or you might be looking at their project and say, oh, actually, you know what, geo might be a really good option here. So it's just about how to have that initial conversation with them, and then, if that works, and then you got to speak to the builder or the architect or something, just how to get those things in place so that to make life as easy as possible for the project itself. What we'll do now is go into a little bit more detail on the heat exchangers. It's going to be a lot of photo-based stuff still, just showing different projects, and we'll talk through them. And probably repeat some of the stuff, so apologies for that for those doing both. But we'll just work our way through them. Please throw out questions, etc., and we'll get it all sorted. Okay, just the objectives here. Just to understand basically what the role of the heat exchanger in the geo system is, or ground source heat pump system is. It's me using different terms again, as we talked about last time. And for yourself, for the participants to be sufficiently comfortable with the technology, just basically start looking at, and getting involved in residential installations. A big part of, if you like, selling the system and getting installed is just giving that comfort to the homeowner, to the client, that you're across it. So this will help to add into that. So in terms of outcomes, once again, be familiar with the concept of renewable thermal energy and its role in the broader economy. I'll repeat again, because I actually see it as being really important. The more we get thermal energy integrated into the energy conversation, the more success there will be in terms of actually making some impact and allowing that to happen. We'll go through different types of ground heat exchangers again, and then we're going to look at some of the interface options coming up into the plant room. We'll talk through some of those, and happy to get some input from others about some of the interactions that they've seen as well. I think the important thing is there's no right or wrong way necessarily to do it. Oh, sorry, I'll say it again. There's not one fixed way to do it. It's obviously it's just got to work. So first thing I do is just look at the annual profile of ground heat exchanger. Then we'll jump into the different types, have a look at the plant room and loop pumps, and then basically some questions again. So let's work our way through. Look, once again, I've just got these pictures up, which we actually happened to finish up with last time as well, for that question on the water loops. So I'll just reiterate, just for anyone new in, top picture there is up in the Sunny Coast area, an open loop system where they're actually bringing water in indirectly from the water body. So they've got almost like a spear pump sort of thing in the sand and the sediments. The owner of this one actually did a company where they did piers and jetties and sand spears and all sorts of different things. So a lot of water interface infrastructure. So he was really keen to do that. That water would come in to a small plant room, through a heat exchanger, and then basically go back out into the canal there. Can be a very simple, low-cost approach if you've got the right conditions for it. Beside that, we have a project down in sort of Mornington Peninsula way, and that's a very large pit loop. There are actually two of those big pits there, and they're basically, so a horizontal pit loop, basically bulldozing everything out of the way, lay all the pipe down, and then bring all the material back on top again, and then it's a nice big grassy open area for the client. Each of those pits are like 90 to 100 kilowatts. So we often work on a rule of thumb about 100 kilowatts per acre in sort of reasonable soil and typical climate for Southeast Australia. Down to the right is actually, we did a series of ski lodges over in Japan using open loop. So, and this became a ridiculously simple open loop. They have potable drinking water in their groundwater a few metres below the surface. Every house pretty much has a little pump, the water board, to do that. And then when the water's used, it runs off into a gully into the rice paddies. So, all you need to do is put an off-take valve basically on the water supply, and then discharge it into that gully that went into the rice paddies. So you couldn't have asked for a lower cost, simpler heat exchange process with that. Unfortunately, obviously, that's not that accessible to us over here. However, just a really good example of what can be simply done when the conditions allow. The bottom is a horizontal loop. You can see here a series of trenches from the Southern Highlands. So, and you can see there in the foreground, also obviously everything's in construction mode. This is not one of my projects or our projects. So Tom was kind enough to share a couple of photos from some steeple jobs. You can see a valve box there, or a manifold box there, where all that pipe work's coming back into that, and then from there there'd be larger header pipes heading back into the plant room itself. So that interaction between where all the pipes go out in the field, come into some sort of manifold, and then back into the plant room, there's obviously a lot of variables around that. As I said before, there's no one perfect way of doing it every time. You pick the best that works for you and that is suitable for the site. The one beside that is a project called Indigo Slam, and that was the one I mentioned before, won like at one point best house in the world, won all the Australian architectural awards and everything, as you could appreciate. And there's, I think, 11 or 13 boreholes underneath that house, about 118, 112 metres deep, I think they are, and a very tight build because previously it was a warehouse, so they had to keep some of the warehouse walls for various height limitations on planning, and one of the walls is kept for heritage, not that you can see there. And so we had to work basically inside that shell of the old factory warehouse to drill the holes to everything else, and that goes down into a plant room down in the basement, and from there obviously distributed heat and cooling through the house. So you can go from obviously your absolute high-end home through to obviously just some very normal homes as well. So you do see a lot of 3-bedroom homes and everything going with geo as well. It's not just all about high-end. Okay, annual profile. This is from one of our commercial projects, a couple hundred kilowatts, maybe 300 kilowatts or so commercial project, but it's one that we produced for another reason, and it gives us a really good example of the storage capabilities of using the ground and when and how like a ground loop system works basically, and why it can become such a useful part of the building infrastructure. So we've got, 0 month is beginning in January through to December at month 12. Blue line is our cooling, obviously high cooling in summer, basically 0 in winter, and the heating following the opposite profile. So in summer, we're rejecting heat into the ground, and that the area under that will be the amount of heat rejecting to the ground. And then in winter, we're basically pulling the heat back out again. It can be basically as simple as that for a ground loop system. Now, as I mentioned in the last talk, vertical loops will do this more effectively than a horizontal loop because of that less interaction with the ambient air. So you will get more storage capabilities out of a vertical system than a horizontal system. We've even looked where storage is a really big part of a project, even things like bringing boreholes closer together and playing with the design so that you enhance the storage capabilities of the ground. Now, that's what we call annual storage or seasonal storage between, putting heat in the ground and pulling back out again. It's in the shoulder periods where it actually even gets more interesting, because what we start to do is you might have simultaneous heating and cooling. We've had projects where simultaneous heating in the building, so the internal building loop is basically self-balancing. So there's net effect on that temperature of the water loop. And so then we put little triggers on the system so that when it starts to increase, because maybe it's getting hotter during the day or something, then we reject back to the ground. Or we reject back to the ground to try to pull a bit more heat out of the ground because it's slowly becoming heating dominant. The reason for doing that is that to minimize pumping costs. Pumping costs are a small part of the system, but they're still an energy user. So we do that where we can when we've got a self-balancing system to minimise the need to go back to the ground to either get more heat or to reject more heat. You also get this sort of approach on in a colder area where it might be a really cold morning, but then by the afternoon or even midday or something, you've got a lot of sun coming onto the building, you need cooling, or maybe there's inner and outer zones of a building where one needs heating, one needs cooling. So what the ground loop does and what the geosystem does is it enables you to basically just keep moving heat around the building instead of creating any heat or anything. You're basically just moving around, storing it as you need, utilizing it again, all for the simple cost of pumping water. The other things it allows us to do is just the heat transfer stuff. So things like, can we also get domestic hot water out of that from the rejected heat in air conditioning? Can we also reject that heat from air conditioning into a pool or a spa or some other water body? So it gives us these opportunities to, once again, just move heat around rather than, creating heat or, having to actually use a lot of energy to do that. Nothing worse than seeing a building where you've got a chiller, a cooling tower and a boiler basically fighting with each other to, try to make it work. Your system efficiencies, in this sort of approach obviously become significantly higher, but also a very hard one to model without doing quite detail on energy model. Okay, so let's go through vertical systems again. We didn't touch on, we touched on this. Do anyone have any, just in the chat, or anyone have any questions on sort of the vertical side of things, just from the previous, or anything they wanted me to touch on? Excellent. Look, what I'll do is I'll just work through it again on this, and then we'll talk a bit more on the projects. So vertical loops by nature are a closed loop system, using the poly pipe to provide that closed loop with the water, water moving through the system. We are able to do that and get that heat exchange because of the temperature differentials between that water in the loop and the surrounding ground temperatures. Just to touch on that again, that surrounding ground temp, particularly below 8 meters, is constant and stable, and it's a function of average ambient air temperature. If you went to, even go to Wikipedia or BOM or whatever, you look at the average of all your monthly minimums and maximums, add about 2 degrees Celsius, and you'll be really, really close to ground temperature. So it's just a rule of thumb, but that's a pretty simple way of getting a sense of what to expect from the ground conditions. As previously, the hottest ground temperatures we've seen have been around the 27, 28 degrees in northwest WA when we've done test boreholes. The project recently in northern New South Wales around the 24 degrees, and Melbourne typically kicks in around 18 degrees. Canberra's very similar, Sydney's about 19. So Adelaide will be pretty similar to Melbourne. So yeah, and also when you get those more extreme climates like Canberra, you do expect it to be that little bit cooler than coastal areas as well. Vertical systems, main benefit of them is that they need the smallest land area. You can't do horizontal and other systems on most suburban lots. So you've got to look at the vertical closed loop system. You do require a drill rig to do that, and that drill rig needs to be able to get on site. That needs to be obviously checked really well, even in the initial conversations with clients. If you have to go to Google Earth or do a drive by the site or whatever, just get that feel for it. Look for power lines, look for trees, look for access down driveways, whatever it might be, to make sure that you can get the drill rig in, including some accessories. Get your driller involved if you need to, and yeah, just make sure basically everything can fit on there and you can do what you need to do. And there's enough space also to do the holes that are needed. Make sure the homeowner also understands it and knows about it, so that they're not, obviously devastated when they see you, tracking a machine across their lawn. Vertical loops do tend to have the highest cost. The drilling conditions, the drilling type, other things will determine what that cost is. We've seen costs range from we often talk about per nominal 100-metre hole, just to give us a simple unit to work with. We've seen costs range from $5,000 or $6,000 per borehole up to, $15,000 for a borehole. So there's, a lot of time your logistics, your travel and everything else are coming to that cost as well. So, be aware of that as a cost element. And as part of the project. So often one of the first things with clients is help them understand what that cost will be. It's the first thing everyone wants to know. So the quicker in a way you can get that client to, you can understand their system and then understand, you know, at least a high level budget and a ballpark, then you can work out if it's worth proceeding both for you and for the client. Most vertical boreholes tend to be, look, I put 50 to 120 metres there. Deepest we've gone is about 125. You could go deeper if you're really space limited. But most instances we've found that range, you know, works well. Borehole spacing, I'll just reiterate that again because it is a really important one. So borehole spacing is effectively a function of that balance of heating and cooling in the system. We showed before on that last image of, you know, you're getting rid of all this heat in summer, you're pulling it back out in winter. You think about that from a borehole perspective, think of it like radial flux of heat. So in summer, that radial flux is moving out, circular waves, or however you want to think about it, moving out from the borehole, and then in winter it moves back in again. What you want to do is obviously make sure that borehole A and borehole B, their radial, that flux don't match, because what can happen then is you can actually start to saturate the ground with heat. In Australia, most of our applications are cooling dominant. So we can have this excess of heat in the ground. So we want to make sure that we get the spacing right so that doesn't become a significant issue. It won't be in the first year or two, most likely. It could very well be further down the track. So I think one of the biggest issues for the industry and with the design side is that if people want to buy a job, they can always short loop a project, basically install a loop that's too small. No, they'll get away with it for a year or two, and then obviously they've disappeared by the time they start having problems with it. So what we want to do is to make sure that we get a properly designed loop that, you know, we can prove and show will still be there in, you know, 50 years time, 100 years time, still operating exactly as it's meant to operate. In terms of kilowatts per borehole, this is another part. So we've had projects range from like 2.5 kilowatts on a 120 metre deep borehole through to 11 kilowatts on a 120 metre deep borehole. The difference is that balance of heating and cooling and the ground conditions. So the worst case scenario is a data centre in northwest WA for CSIRO. Some of you are possibly familiar with that through air or through other things. Ground temperatures are 27, 28 degrees. You've got a data centre, so you're basically, you know, heat rejection only. So the boreholes are spread out massively, 24 metres or so distance, but all you're ever doing is putting heat into the ground. So therefore your capacity per borehole, your sustainable capacity per borehole is very small, like 2.5 to 3 kilowatts. And in fact, that was over a 15-year period. We worked with CSIRO to model that over a 15-year period because that was enough for that building as they were doing further stages of the building. The better case scenarios are when you have a balance of heating and cooling in the building in a climate that's got a much better ground temperature. So our 18 to 20 degree ground temps that we have in a lot of the country, or in the southern half of the country, where a lot of the population are, they enable us to have 18, 20 degrees is a really nice place to start with for heating and cooling. Also, when you get a building that's well balanced in terms of heating and cooling loads, you basically have a natural balance in the system. So the amount of heat you put in summer, you know, you pull it back out in winter, and there'll of course be overlaps at other times of the year. That allows us to bring the spacing closer together. Could be around the 5 or 6 metre mark, for example, and allows us to get, you know, 10, even the best we've seen is about 10 to 11 kilowatts per borehole. And that's on a really well balanced system, you know, well designed, etc. I think I mentioned earlier, some of the earlier systems were like about a 4 metre spacing. That can be okay. It just depends on the overall system and the long-term usage of that building. Residential systems are a little bit less critical in terms of spacing because there's usually, in terms of at least the Australian way of utilising aircon, there's a lot more rest in the period. Whereas a commercial building could well be, you know, 24/7 operation in terms of heating and cooling, so movement in and thermal movement in and out of the ground. Residential systems will have a lot more rest. You've got a lot more opportunity, if you like, for the ground to to passively relax and to allow heat to move away from it. So you often don't need that as big a spacing on a residential system. Okay, let's just talk through it. So I'll talk through some of the challenges on the various sites, just to get a sense of obviously drilling conditions, etc., and then some of the design elements as well. So top left, Chippendale, Central Sydney, near Central Park there. Obviously looks very different there to what you saw before. I think, well, photos are taken on good days. Once again, it rained the majority of that install, so it became very, very busy within that old warehouse area. The boreholes on the main building were about 110 metres deep, because we had to go that to the deeper end to fit inside the area that was available to us. Over on the right, for example, became a wine cellar and plant room as a basement level. So we didn't have the full building footprint to work with, and we had to work with other building footings and all sorts of other things as well. So when you're working underneath a building, which you'll have to at times, obviously, as well as all the other coordination checks, make sure you get a sense of all the structural elements of the building as well, so that you're working in with that. This is all Sydney sandstone, so good thermally, good water content in the rock, a decent density in that rock with the sandstone, the way it packs together. So pretty good to work with, relatively pretty easy to drill. Drilling method used that wouldn't result in lots of water production at the surface, so water could mostly be recirculated through the drilling process. We managed to hit a dike at some depth down here underground. That caused some, it was only like a metre wide or something running through the site. So the guys were pretty impressed that they were able to find that. Not very happy, of course, it caused a bit of problems. And that was at, I don't know, 70, 80 metres or something. It was pretty deep down. So even though the rest of sandstone is usually, sandstone is quite massive, you just sort of work your way through it, get through some rock fractures, you still can get some, some oddities that happen where, we're working with nature and the environment after all, so it doesn't always play the way we'd like it to. Below that, just a smaller residential 15 kilowatt system, 3 holes, about 75 metres each, just on the outskirts of Sydney. So we're in Sydney sandstone again. You can see all the bushland there that a lot of people would recognise. Nothing was happening on the site at the time. It was an empty block of land, so we could just go in, put the holes, obviously in the right spot, work that out with the builder and survey them in, drill those holes, and then get off site. One of the things we talked about in the last course, get your drill rig in there and get away before everyone else comes in. And then we left those boreholes there and then came back and joined them up, and then, connect them into the plant room. Geez, it was potentially even 12 months later. So that's where you also need the builder on your site to make sure that they're not, that they're going to look after your boreholes for you. So, bury them, put them on the gator covers, do whatever you need to do to make sure they're, not going to get damaged. We have had builders basically damage pipes, and, you come back to install them and and there's some damaged boreholes there that need to be repaired or even, basically cut out of the system, decommissioned as such. So it is important to get them looked after over that period of the project. That comes down to what we talked about before about, that communication with the builder and working with them. But yeah, 3 75 metre holes for about 15 kilowatts. And yeah, just a simple fly and return headers, reverse return headers going back into a plant room. Yeah, Sydney sandstone again. So a lot of rock fractures in here, to the point where the drillers actually went over the cliff edge to see if some of the grout that they were pumping down there was coming over the edge of the cliff. It wasn't, but it did mean that there was some, they had to allow for more grout than they expected to, make sure we obviously fill those boreholes properly. The middle one is one I mentioned previously. That's a sonic, what's called a sonic drill rig, and sonic is basically a high vibration frequency sort of drilling method that just pretty much just vibrates its way through the earth. We utilise that on this project in Canberra because we had to go through some basalt and then a granite underneath that. So, and in that basalt was a lot of water. In fact, just 20 metres from the drill rig there is a water bore on this site that they use to irrigate the gardens and lawn, sporting fields, etc. So There was a lot of water produced through that, so this method allowed us to, to kind of avoid that without having lots of water produced at the surface and then having to dispose of it. Granite and basalt and stuff, they're your harder rock types with a high water content. They can still be really useful thermally, just obviously requires a different approach to the drilling itself. The good thing about a lot of the rock drilling is that you will typically get a very clean open hole to work with. So there's still got to be some, depending on the rock fractures, some management of that hole, but a lot of the time you'll have a really clean hole. The loop will go down really easily. Very little issues with that. Top right is Western New South Wales, northwest, I guess, but Western New South Wales. Obviously pretty dry out there. It was really just a pretty unconsolidated sort of material, not a hard rock at all, a lot of siltstone, limestone sort of layers. The ground temp here, this is just set up for a test borehole here. Ground temp here was about 24 degrees. So, and we're in a cooling, even though it's obviously quite cold out west, still very much a cooling dominant climate. So that will end up with, kilowatt capacity per borehole. I think it's around the 4 to 5 kilowatts. I'd have to double check that, but once again, we're at the lower end of that because we've got a cooling dominant system in a hotter climate and a hotter ground condition. So obviously you're trying to reject heat into an already relatively hot environment. So there's less ability to do that. It was also very dry out there, 120 meters deep, but very dry, which meant that we didn't have that water to help transfer the heat away. So you do have a, I guess in a way, relatively or a lower performing borehole in terms of kilowatts, per borehole. So if you ever see, people out there saying, oh, we get X kilowatts per borehole on every borehole or some sort of rule of thumb design or something, essentially it means they fundamentally don't understand how the technology works. Because obviously we need to work with the ground, we need to work with the environment there, with the soil type, with the temperature, with the soil moisture in order to get performance out of the system. You can't brute force nature as such, which is often what they'll try to do, or they'll be massively oversized or undersized. So, you need to get those systems done properly. And you need to get the design done properly, that understanding of the ground done properly. And bottom right is a northeast Victoria, out in the river plain areas. So bigger drill rig here. You see some of the bigger requirements a little bit off in the distance. I think photographer was trying to be artistic with getting that loop. That front is a ground loop with a little bit of PVC casing in there, that 2 bits of pipe sticking up. That PVC casing will be removed, and then that loop will be cut off at the surface, cut off below the surface once the trenching's set up for the headers. The conditions up here, this is typical floodplain conditions. So you had, and these were like what was called mud rotary drilling. So floodplain conditions, you can get through just like think of it like an auger, if you like, a hand auger, a mechanised variation of a hand auger, pretty much just working its way down to the ground. It is circulating the drilling muds through that system, and the drilling muds are used. They're usually a form of bentonite, but there can be all sorts of other things in there that are used to keep that borehole open. So the borehole can run the risk of collapsing on you. So you need to make sure you've got a driller who understands their muds really well, is able to drill a hole, leave it open for long enough for you to get that ground loop in and to grout it up. And the reason that we grout on all our boreholes is number one reason, actually, environmental protection. We don't want to be cross-contaminating aquifers because we're going to the depths where we can do that. We also don't want surface contamination to come into the groundwater and contaminate groundwater. So we do look to completely grout up the entire borehole column. It also removes air pockets to make sure that we don't have any air pockets down there, which will obviously impact on the performance of the system. And it's important that we don't get bridging. So when we grout from the bottom up. We don't grout from the top. Obviously, you end up with bridging and it won't all get down. Also removes that ability if you get little layers as you go down through rock fractures that might come on in and bridge halfway down. So your drillers should be able to manage all that for you. Your role, if you like, as the guy on site, if you're supervising them or just checking on them, is to make sure that they're giving you what you need in terms of getting that good connection all the way down to the ground and to full depth. Okay, a couple of images here. I think this is out the back of Canberra again, actually, the two outside ones anyway. Just showed here, look, there are all sorts of ways to get the loop down to the ground. Just got here a simple pipe roller, 2 poly pipes on either side, 2 pipe coils. They've been pressure tested, flash card on the left. Most of the pressure testing, the standard, if you like, is 100 psi for about 20 to 30 minutes. Basically, flush all the, that's just a classic flash cart, which a lot of you probably have for your hydronic systems and things. We're just looking to flush that ground loop, get all the air out of it, and then pressure test it. So get it under pressure, that 100 psi for about 20, 30 minutes. Sometimes the drillers will be able to do that for you. Other times you'll have to do that sort of thing. So what we'd recommend is, and you get that signed off, even get a witness off a client if you can, so that you can show that obviously everything's been pressure tested properly, because obviously once it's down and in the ground, then it's there for, you're not getting it out. So we want to make sure that we've got, good integrity of that pipe system, and also check that water flows through it properly as well. So even after it's installed, and even grouting back up, just run the water through it again, making sure you're still getting a good flow rate through it and making sure it holds pressure. So the pipe is tested at the surface, installed, keep it under pressure if you can, grout it up, keep it under pressure, and then maybe do another flow check as well at the end. And then you can be comfortable that the integrity of that loop is good. You can see on the right-hand side, the guys are just pretty much installing that one manually. There are, like most drillers have their own setups. There are some, obviously come off a pipe roller, putting it in. There are some mechanized pipe rollers that'll run a little motor to help put it in the ground. There are some with, brakes on them and all sorts of different things. So there's a few different options to do that. Just realised, I thought I had a photo here. I don't. Also, often what you'll find on the end of that ground, what's holding those 2 loops together or joining them is what's called a U-bend. A 180-degree elbow is, I think, technically what the various manufacturers call them. But basically, it's a U-bend that's welded onto the, to join those 2 loops together. That's welded on there, and that's essentially what you're pressure testing in the system. You're making sure that that weld's good. Obviously, every now and then, I've had once or twice, we've seen a loop turn up to site and a forklift or something's punched a hole in it. Pretty rare, but also you're still obviously checking the integrity of it in that respect, making sure there's no leak or anything in the system. We don't want any other joins in that system. We just want that single one at the bottom. You can get some factory fitted join systems. Some of the crosslink poly pipes will actually pretty much have a bend in them themselves, or you can put the fitting on yourself on site. So it just really depends on how you want to do that. And then on the middle there, we've just got a grouted up borehole. So obviously all the slop, if you like, at the surface is really that grout as that grout's pushed up. There's your bottom up grout. So when you install that loop, hard to tell on the one on the right, but up in the top section, you can see that there's actually a second or a third pipe there, or a third loop. That's a tremie loop that we're pumping the grout in. They'll get installed with a loop, be taped to the bottom of the loop, and there's a weight on the bottom of the loop as well, which helps to get us like down to the bottom. When you've got a lot of water in the hole, the water will give you a lot of buoyancy. This becomes really hard to get over. It's the other reason why we fill the loop first with water before we put it down. You'll never push past the buoyancy point once you hit it. And you'll know when you hit it too. You'll think you're at the bottom, and then obviously check the markings on the pipe, and you're nowhere near it. So we do need to overcome that buoyancy. That's probably the hardest part or the trickiest part in terms of getting the loop down the hole. But then once that's grouted up, the tremie line just gets pulled out as you go. We ideally not keep it in the hole. And then of course that grout will then start to push any water or anything in the hole up to the surface, which you'll need to manage. And then you'll end up with what you see in the middle there of the grout. Basically, you're sitting at the surface, and it'll take a couple of times to settle. It'll still drop a little bit, and then it'll be it'll all be right near the surface and good to go. Remember that you are trenching to join these boreholes. So if that grout ends up settling, within a couple 100 mil of the surface, then that's fine. You don't have to get up to the surface and everything. just keep an eye on it and make sure that it doesn't settle and get away from you. You can do that even overnight or over a couple of hours. So it is definitely worth watching it to make sure that you've got that good, good grouting connection on the system. If there's any questions there on vertical at all, please feel free to reach out. Just grab me a quick glass of water. Okay, horizontal loops. A variety of ways of doing a horizontal loop. Once again, we're talking about closed loop systems here. Horizontal loops mostly will need 2 acres plus. You can sometimes fit them onto a smaller block of land for a smaller system. Keep in mind with horizontal loops, always check with a homeowner what they may or may not be planning to do in that area. You don't want to put that in there and then find out that that's where the pool was supposed to go. Horizontal loops also shouldn't be under a sealed surface. Horizontal loops work by their interaction with the ambient air, more of an interaction than the verticals. And they can work okay on heating. So often here, in Europe, they put a horizontal system under a car park. What they're doing there is that they're basically extracting the heat or absorbing the heat out of the bitumen layer, allowing that to come into the loop and then back into the building. Our problem here in Australia is that we're rejecting heat out in summer. And can you imagine rejecting heat out in the surface car park or something is about 50 or 60 degrees? Then our heat can't escape from the ground loop. And what's going to happen is that it's just basically, you've got this big thermal blanket over the top of it. It's just going to cook the ground. What happens first is you dry out the ground. Ground starts to crack then, becomes more friable, and it's heat saturated anyway, so you won't be able to discharge heat into that area. So a horizontal loop could, sneak under a driveway or, go underneath something at some point, which is sealed, but it should be a really small part of the overall length of the loop itself. Even ask things like if the homeowner, are they about to plant trees in that area, or if they're going to put a veggie garden there or some roses, we're at 1.5 meters deep, so that's probably fine. If they plan on planting all these big trees in that area, deep-rooted trees, tree roots will take the easiest path available to them. So there's every chance that they'll end up inside the horizontal loop area, inside the trenches, because obviously that, even though you've backfilled it and done some compaction and everything, it's still not as firm as the ground around it. So yeah, you're going to need obviously an excavator or a backhoe. We haven't seen some bulldozers on some of the larger pits to create the area available for you. So yeah, need to make sure of obviously what's available there. Make sure there's a good conversation with the homeowner on what's going to be there at the end, the expectations. You're supposed to leave them bowling green, or if it's in the paddock, can it just be a slightly raised trench area that with a bit of rain and a bit of settling will be back to normal and grassed within a few months. Expectation management is probably the biggest part of putting those in. Soil type and moisture, I mentioned this before, but yeah, absolutely critical, the horizontal loops. I'll use the same example, a dry sand versus a wet clay. That dry sand could need up to 3 times more trench length or loop length than the wet clay, purely because you don't have the density of the clay and the moisture to help draw and transfer heat away from the loop. Soil depth, a lot of time around the 1500 mil mark. We look at that, that's our standard LHS depth. It also gets us down into that ground temps that are becoming really, really stable, plus or minus about a degree. So we've got, we don't have much interaction at all with the surface. If you need to go higher because of shallow rock or something like that, you need to go longer on the loop. We'd recommend not going above 1 meter if you can help it. You do start to get up into the sort of a little bit too shallow when you get above the meter mark. And remember, this is on the main horizontal runs. When it's just your headers, then you can be 600 to 1 meter. That's okay. On the main areas, we want to be around that meter to 1500, preferably around 1500. Pipe spacing on pretty much all horizontal systems is around 300 mil. So if it's a big pit loop up and back, or it's a trench, we still look at a similar spacing. And that can be vertical as well if for some reason it's layered. main benefit of horizontal over vertical is just a slower cost to install, but of course you need the land area to do that and the soil depth. Okay, same images as before. Bottom one, I actually talked through these a bit before, but so this one is a bottom left is a pit loop. So your classic big rectangular pit loop. As I said, there were two of these on this project. You can see all the main header runs coming in on the bottom of the picture of the photo, and then our flow and returns heading out. On this pit loop, what we've done is we've then gone out into the 25mm pipe, which is the main heat exchange part of the process. It goes down to the end of the pit, which is about 100 metres away, turns around and comes back. You can also do pit loops where you come in at one end like this, and then come out the other end, and then run a header line back to the, back to the plant room from there. It can be sort of a one-way or a two-way arrangement. Usually site logistics will determine that. Soil type obviously important. You can see here some pretty reasonable clays, silty clays in there, and then that was all backfilled over that. Obviously make sure you get all your lines nice and neat and separated and everything, so you don't have interference on the system through its length. The one above that is Southern South Australia in limestone. Limestone is one of the few instances where you will probably have to bring in bedding sands. Look, ideally, let's utilise the same material that was there that we dug out. Stockpile it, put it back in the hole, track it in, compact it in, and allow it to settle. Where you can't do that is things like limestone, because it's it's craggy, it's rocky, it's sharp. So bedding sands we utilise on this project. This one is a 6-pipe loop, but in 2 layers. So 2 layers of 3 to make up the 6-pipe loop. And normally the way you configure the circuits within each trench just depends on the bucket that's available in the excavator, and maybe on the area that you're working in. So this one's 2 layers of 3 with backfill in between. Look, that's a lot slower because obviously you've got to wait for all the backfill to happen and then come back. So if possible, suggest look for a wider trench so that you can get more in the bottom of that. One on the top right is nice red soils down Mornington Way. Once again, they've used those 6-pipe what we sort of term the geo hands, running out, and then and they're just laid out at the moment. They get buried in later. But you can see the 6 pipes running off in through those trenches. I thought we had a close photo of that, but the other thing you can do is you can put 3 or 4, even 5 pipes on the bottom of the trench, and then you can just get some pegs or some supports of some sort, and then put some of the circuits on the sides of the trench, and then sort of peg them into position. And normally, to keep all the pipe work aligned, all we do is just walk through there with a shovel and just align everything up with a bit of shovel on it to weight it all down in every 10 metres or whatever's required for that area. But so you get those 6 circuits in. Look, most of the systems we look at horizontally are a 6-pipe arrangement in that respect. Some can be 4, some can be 8. They're almost always 25mm. Every now and then there might be a 32mm pipe. Just a few of those variables that come into play on that design. And then that one on the top right there, obviously just backfill from there, nice clean soil. And then you can see we're starting to get the fly and return headers heading back to the plant room. And then the bottom right, rockier, a little bit rockier, but still fine to work with. And you can see there just where we're coming back up to where the manifold is, if you like, on that with those geo hands, and then a fly and return just heading up into the plant room. This is one of the approaches with your manifold, where you go from multiple smaller circuits into your header return, and these are just buried in the ground. They're obviously marked, so if we ever had to go back there, we could find them again. But everything is buried, which is where the electrofusion obviously comes into play, very much so, and it keeps everything nice and nice and neat and simple in the ground. It does mean, however, obviously you don't have that easy access to them. The whole systems are designed from a pumping perspective to be self-balancing, whether it's use for those hands there or like a reverse return. So you shouldn't need to go in there and do anything to modify flow rates. In terms of water loops, yeah, I've mentioned before, water loops are obviously unique. You have to have the water body there, whether it's surface water or groundwater. We are a very dry country, so we don't see a lot of them. Even where there are dams or something available, let's make sure that it's going to last, that it's going to be there a long time. From a cost perspective, typical cost to a horizontal loop for the closed loop water loop systems. For the open loop water loop systems, they can go from being ridiculously cheap to incredibly expensive. It all just depends on your ability to access that water and to utilize it. Closed loop systems, we want a nice, reliable 2 meters plus depth of water. It's got to be a certain size to match the heating and cooling requirements of the build. If a dam was less than 1/4 of an acre or so and without good depth, it's probably not going to be as reliable as you would like it to be. So it does still require a decent sized water body. It also depends on turnover. If that's spring fed or water's flowing through that regularly, or if it's the water's refilling it regularly and they're using it for irrigation or turning that water over, then obviously we're refreshing it so we can get more capacity out of that same volume of water. Closed loop systems can be polypipe, as in what this image shows there. It's basically just 25 mil coils, and join them together in parallel, and then run the flow and return headers back into the clean room. Or we can do a similar thing with plate frame heat exchangers, whether that's in stainless steel or titanium. So there are a few options there on how you go about it. The coils are obviously easier to access. You can just get them from your local plumbing supplies or pipe supplier. The plate flame heat exchangers need to come out of, obviously, specialist manufacturers. More expensive, but may have savings on installation, etc. for that. So there's a few pros and cons of that to look at. Typically on a smaller installation, the polypipe is probably the way to go. On larger installations, where you start getting really complex and needing a lot more surface area for the heat exchanger, because it's because it's just so much larger, and the plate frame heat exchangers could well be a better option. Open loops can be surface water or groundwater. In terms of surface water, if we're looking at that farm dam that's there, the limitation with open loops is that you need to have them you can end up with a lot of sediment, a lot of muck in the the water body that you've got to deal with from a maintenance perspective. So really be aware of that if you're looking at an open loop system. It comes down to the 3 rules of open loops: is sustainable water supply, water quality, and can you get rid of the water? So we've looked at open loop systems. We were talking about one earlier on up around the Sunny Coast Way, where that was accessing that canal water indirectly. We've looked at them as spear points, on back sand dune areas, or maybe if a house in the country or a floodplain area has is they're using water bores, then you could even tap into their existing water bore. So, which obviously wouldn't be that expensive to do. So there's a few options to look at that. Once the water's been used in an open loop, we can use that for irrigation. We could use it for as a grey water almost for flushing toilets or something. The water can be used again, which obviously has some, in water scarcity areas, has some good benefits. That was, for those who have come across the Cool Earth project, which is a project we did over in WA with what we then call Landcorp, University WA, which is a WA state developer, and University WA did independent monitoring of that. That was a open loop using the groundwater. It was about 50, 60 metres deep where we had to access that groundwater. The suburb or the location was a little bit higher. A lot of Perth is a lot lower. Often you only have to go 5 metres or 10 metres to the groundwater. That water's pumped up. And then basically there was an option there to look at subsurface irrigation before rejecting it back into the water bore. In that instance, we actually rejected into the water bore vertically. So we use the same bore. So we extracted out at 50 odd metres deep. We rejected the water back in at about 20 to 30 metres deep. We're still in the top of the aquifer. with the theory being that by the time that water, which was moving, groundwater is moving sideways, it had the ability to get away, and therefore it wouldn't recirculate back into the same system. Otherwise, typically you'd have a second bore, which is a rejection bore, which you have to pump the water up out of one, reject it back into the other, as per that drawing. Distance between those bores is really important. We need to make sure that we can't basically circulate in between the two, and then therefore obviously cause our own little closed circuit of ever colder or hotter water. And sometimes water bores, if you're really shallow, you can release, like the Japan example I mentioned before, local regulations, local authorities allowed you to dump that water to a surface drain, which is either then going to just absorb into stormwater and into the ground, or in that instance, head down to the rice paddies. So be really aware of local regulations. Water bores typically need a license. So you've got to make sure that all those things are being considered and allowed for in the early stages of the project. Okay, so the plant room, bottom left, we've got 3 boreholes, Southern Highlands, and this is a pretty old project, this one. Basically 3 holes in a straight line, reverse return header, heading back into the plant room. So the ways that you can manifold the boreholes and join them together is either in the ground in a trench as a reverse return header, or you can bring each borehole independently back into the plant room. So continue, say, the 40 mil pipe back into the plant room, and then manifold them back there. It usually just depends on partly what you're familiar with and prefer. Also, sometimes the site will determine what's the best requirement to do that. On the top drawing there on the left, you can see all the electrofusion fittings with going into the ground and the reverse return set up there. For those not familiar with reverse return, it's basically parallel flow into all the boreholes and it's self-balancing. So therefore we don't need to worry about extra valves or modulating flow or whatever else you might need. So it keeps everything really, really simple, which means that there's nothing mechanical or anything else in the ground. Everything is just basically polypipe in the ground with water flowing through it. You can see on the top right, we've got a little building penetration, which this is the existing structure. So it had to go, basically that was the only place we could do it. Where that would have been sheltered, insulated or whatever, because you got a little bit of exposure there in a cold area. Otherwise, everything else is obviously underground or then back inside the building. On the bottom one, we can see a flash cart hooked up to a ground loop, which has come through the building penetrations. So those penetrations would have been done obviously before the slab pour. And then we've connected the ground loop to that outside the slab, and then it's been pressure tested and flushed at that point inside the plant room. So obviously really important coordination with the builder for that, for that part of it. Okay, different types of manifolds. The one I mentioned before, we just have each borehole comes back to the plant room. You can just see a typical off-the-shelf manifold there for that. You can run, the reverse return headers in the ground. Or the one on the right is actually the reverse return headers in the ground. This is for an apartment complex, but it's reverse return headers in the ground and then the manifold system inside the plant room. So you've got a combination of things. None of them are, there's no one size fits all. None of them are, more correct necessarily than the other. Comes down to what you're comfortable with and familiar with. Those little manifold boxes and valve boxes can sometimes be outside. You can put a little pit in the ground, a little, manhole or man cover or whatever, depending on how big it is. So you do have options to do that either outside or inside the plant room. Just obviously make sure that anything outside is, protected, it's accessible if needed. If there are, any valves or anything on there or ports for monitoring. Otherwise, everything's back in the plant room and easily accessible. And ground loop pumps. Look, pumping strategy is really important to overall performance. It's, it should be less than 3 to 5% or something of the overall energy usage of the system. It should be really small. but we do regularly see issues where pumps are just sized badly and then the system just doesn't work. The whole system, the performance of everything, I said in the very start this morning that it's embarrassingly simple technology at times. It's just about getting the right water flow through the ground. If you haven't got the pumping strategy set up properly, it won't work at all, or you'll have all sorts of issues with it, and poor performance, which, for the fact that homeowners just paid for all these boreholes and all these systems, and then, the simple part of getting the pumping wrong is obviously pretty, a pretty silly error to make. Sometimes in terms of the ground loop pump, there'll be a pump internal to the heat pump. I put that check with the Siebel guys. Obviously, in terms of the individual heat pumps, some will have internal, some won't. If they don't have an internal pump, normally those internal pumps are, and maybe one of them can confirm, they're often variable speed, so there will be a bit of option to pick, a little bit of variation in different in different ground loop designs. Otherwise, we've got to look at installing an external loop pump. On the left, we've got little things. There's more a North American approach where they actually have flow centers. So that box sits on the wall. It's got a couple of Lagrange-Foss circs in it, and it's got some three-way valves in there as well for, pressure testing the system, flushing the loop, that sort of thing. On the right is obviously a much bigger, that's a home. They've just got a whole series of floor-mounted circulating pumps. That'll all obviously be tuned and organised to work with the ground loop, and some of them probably are going through the house as well. They may not be all for the ground loop, possibly some N+1 redundancy in there as well. So yeah, pumping is critical. Understand your pressure drops across the system. Pressure drop across the ground loop, I think should be somewhat equal to pressure drop across your heat exchangers and your heat pumps. Just make sure we get that bit right. Otherwise, you just have a bad performing system for what should be, an hour or less of design, or a couple $100 on a circulating pump that, can mess up tens of thousands of dollars worth of installation. And that's it. We'll finish in the plant room. Seems an appropriate place to finish. Please, any questions or anything else in there?
I don't have a question, Yale, but that was really informative. Really appreciate.
Thank you. I hope that's okay. So I'm going to just sort of tell the story through the photos. I hope that was okay, so people could see that. I always find it's easier sometimes just to see real drops rather than pressure drop charts or whatever else. Aren't always necessarily the best way to do it.
No, exactly. I think the easiest way for installers to get some scope on how they then transfer that information to the clients is to see it visually.
Yeah, that's what I found. So yeah. And then of course to go and see stuff, go and touch and play with it and get to understand it.
Yeah.
Yale, I got a question about the loops and
yep.
And you were mentioning that the systems, the ground loops are self-balancing, that you have equal flows and so on in your manifolds. Can you just go over that in a bit more detail, just to know how to achieve?
Yeah, look, that's and I just saw a chat up there as well, so I'll answer that after. Yeah, one of the simple ways, and I do see different approaches, and so the technology developed in sort of Europe and North America kind of simultaneously, so there are some little variations in between the two. Residentially, one of the, particularly the North American ways, was to not have anything outside the house that's, requires, you don't have to touch anything basically. You put it in the ground, you just leave it. So a lot of time what that meant was making sure that anywhere where you obviously have parallel flow, but to make sure you have that reverse return header on that system so that everything balances out naturally. And you even size your piping diameters and everything so that you minimize your pressure drops and your pumping requirements, but also so that you get that balanced flow. Just kind of considered better, if you like, than having to go and, you know, play with modulating valves or whatever it might be. The reverse return header basically is such that when you come in, so the very first borehole, water flows into that, and then when the water comes out of that borehole, it actually continues away from the plant room right to the end of the job, and then comes right to the end of the boreholes, and then runs all the way back again. So you kind of, it's like first in and then last out. It's really hard to I find it really hard to describe verbally. I think just a Google image on that and you'd find it, and it makes sense pretty quickly.
Yeah, first in, last out. That's how it's done also with regular plumbing, and then you get equal flows through tanks, for example. It's just that with plumbing particularly, the more you have, the more devices you have where you need to do this, the trickier it becomes to do the actual balancing. And on occasions, depending on the system, you may have to put balancing valves and things like that. That's why I was wondering, you definitely don't want to have anything that requires any maintenance at all, you set and forget sort of thing. That's ideal. It just seems like quite the feat actually to be able to do that with such large loops and you know, so many of them really.
Yeah, look, considering most residential loops are, you know, 15 to 30 kilowatts or so, it's not too difficult at that scale. I know, you know, when our tech guys and our engineers are working through it, they do put, you know, comparatively large amount of effort into understanding all the pumping and flow rates as they do in, you know, in other parts of the project, because it is so critical. I do see when you do but then I've seen, say, on a lot of the European approach is often they'll bring all the boreholes into the plant room individually, manifold them in there, and then they'll have, you know, the ability to turn them on and off as they need. So there is different approaches to it. I think it's almost like just a bit of a cultural difference between them. But I'm sure they're both, you know, could argue quite vociferously as to why theirs might be better or worse than the other.
Yeah, sure. Thanks.
A question on the kilowatts per meter of various soils. Yeah, look, it is awkward. Sorry, so it's not necessarily an easy question. On a vertical system, we typically, so I think I gave the range before, if we've had, you know, systems with 2.5 to 3 kilowatts on 120 meters worth of borehole, and other systems with, you know, up to 11 kilowatts on 120 meters worth of borehole. The ground conditions will affect that. But what affects the ground loop performance as much as anything is also that balance of heating and cooling and the usage from the building. So it really is integrating the two together. The base rule of thumb we use on residential, trying to be a little bit safe, if you like, because when you're first speaking with a client, you want to be able to say, look, you'll need, you know, 6 to 8 boreholes, and therefore do we have the area and that sort of thing. You basically want to be able to do that at least. 5 is a safe number for 100 meter bore. Probably squeeze a little bit more than that out of it, but that's a pretty safe number when you're first doing those initial sort of high level feasibility stuff. I wouldn't go above more than about 7 or so on a residential, and also keeping in mind that it does have a decent balance between heating and cooling cycles. Horizontally, it almost even varies more because you've got that extra influence with the ambient air temp. We often see so if you only needed 5 or 6 kilowatts, then you might be, say, 100 meter trench. Typical 15 to 20 kilowatt system could be in the 250 to 400 meters of trench, depending on the obviously the soil type, the climate, and the requirements of the building. So there is still quite a bit of variability in that. And if that was a dry sand, it could be 800 meters of trench or something like it. We obviously hardly ever look at dry sand projects. It's just not that viable. Is that okay, James, in terms of answering that? Cheers, mate. And also, project is ground cost competitive. Yeah, really good question. It depends. And I feel as if I answer nearly every question with it depends is my like precursor. What makes ground source work compared to anything, if you like, is a combination of things. Where it's most viable, and it's actually probably something that we should touch on a bit more, is looking at usage. If someone just turns their aircon on for a couple of hours, a couple of times a year, you may as well do air source. They're not going to use it enough. The more you use it, the more you save sort of mantra. There need to be people who are going to get decent usage out of their heating and cooling system. So if they're in coastal, northern New South Wales or something like that, people there tend to not use aircon a lot. If you're in Canberra or other parts of further down south and you use your aircon a lot, then obviously you're going to get more usage out of it to enable it to become more competitive. The other areas where it becomes more competitive is the type of ground loop. A vertical system makes it the hardest to be competitive because it just costs more. So if a client is looking at simple paybacks or anything like that, the vertical system will be the hardest one to get across the line with them. Often it means you're in a metro area. And if that's in a coastal area or something, then obviously it's harder again because they're not, they're just not going to be using the system as much, or potentially not using the system a lot. Be careful as per the end of the last call, every client is different and wants their own thing. So you got to make sure you understand, what they're doing and how they're using the system. So cost of the ground loop versus obviously cost of conventional, that's your big difference. That's the bit where if you can obviously bring that down without short looping, but if you can bring that down through horizontal or through whatever, then obviously you start to become more cost competitive. If you're in a climate where they're utilising the system more, just because of general usage, also because of more extremes. So if you're in a climate that's regularly below zero, and these people are heating their home all the time, and air sourced isn't going to do as well with that as the ground source will. Ground source really won't lose its efficiency. Very rarely will it get below, say, a COP of 4. They don't have a defrost cycle. They don't overheat on a rooftop on a 40-degree day and it's 50 degrees or more on that rooftop. They're not being belted by that sun. You might be in a corrosion area where, coastal area where air source units also lose their, efficiency pretty quickly over time as well. So there's a whole lot of factors that come into play. Size is just a part of that. We've seen some really competitive 5 and 6 kilowatt systems because we could fit in a really easy loop on a small block. And that might even be while they're doing other excavations. The other area is the mix of heating and cooling. If they've got a pool, they've got heating, cooling, hot water, and a pool, you've got all these different usages, then we can do more with that to transfer heat in between all of those different requirements. Get those, as per that first diagram on the that graph I showed on this talk, those simultaneous heating and cooling requirements where we can basically load share and just move heat around a building instead of having to, create new heat. They're the things that make the system cost competitive, not so much the size on it as a standalone. Cheers. I see time's for any other questions in there. Obviously, happy to reach out or through Steve if there's any other questions on on anything. Hope it was useful. Appreciate the opportunity to talk through it.
That's awesome. Really appreciate you chipping in and providing a couple of sessions for the customers.
Yeah, no problem at all. We love talking about it and seeing more installers involved in the industry. So anything we can do to help with that.
Fantastic. I'm going to take off. Thanks again, Yale. Cool. Appreciate it.
Great. Thank you, everyone. We'll leave it there if that's it.
Thank you, Yale. Very appreciated.